Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll examine several illustrated examples of series DC circuit analysis. This lecture operates under the presumption that the viewer has more than a passing familiarity with series DC circuit properties, including Kirchhoff's voltage law, and can wield the DC voltage divider rule without cutting themselves. If you lack the requisite level of familiarity with these topics, please review the supporting material at the Big Bad Tech channel and return to this lecture when you are so qualified. Mastery of series DC circuit analysis necessitates active participation on your part. I'm encouraging you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers do not match those illustrated, by all means, feel free to rewind the lecture and correct any mistakes you may have made. Our first illustrated example features a 36-volt source in series with a 560 ohm resistor, a 910 ohm resistor, and a 300 ohm resistor. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. Additionally, we're being asked to solve for unknown voltage Vx with the indicated polarity. By all means, pause the lecture and try this on your own. Present all answers in proper engineering format, rounded to the 10th place. If you're tracking, you should have obtained the following results. Before we begin the analysis of the circuit, it's perhaps worth a moment of our time to review fundamental series circuit properties. First, current through elements in series is the same. This is the most fundamental series circuit property. For this circuit, source current equals I1, which equals I2, which equals I3. If we solve for current through any series element, we by extension also solve for current through all remaining elements. Additionally, Kirchhoff's voltage law states that for any closed loop, the summation of voltage rises equals the summation of voltage drops. A Kirchhoff's voltage law analysis of this series circuit, starting here and traveling in the clockwise direction, suggests that E equals V1 plus V2 plus V3. We'll examine unknown voltage Vx in a moment. Additionally, we should expect the largest resistor in this series circuit to drop the largest amount of voltage and dissipate the largest amount of power. Conversely, we should expect the smallest resistor in this series circuit to drop the smallest amount of voltage and dissipate the smallest amount of power. Finally, power in always equals power out. For this circuit, Pn equals P1 plus P2 plus P3. There are several ways to obtain the desired figures. Perhaps the easiest, most direct means of doing so is through the use of the DC voltage divider rule. The DC voltage divider rule, set up to solve for V1, suggests that V1 equals R1 divided by R1 plus R2 plus R3 times our total supply voltage E. Substituting our given values yields V1 to be 11.4 volts. We could use another implementation of the DC voltage divider rule applied to the remaining elements. However, let's make use of Ohm's law. Current is equal to voltage divided by resistance. Substituting our given values yields I1 to be 20.3 milliamperes. Current through elements in series is the same. This is the most fundamental series DC circuit property. I source equals I1, which equals I2, which equals I3, and they all equal 20.3 milliamperes. Another implementation of Ohm's law demonstrates that V2 is 18.5 volts. We could use another implementation of the DC voltage divider rule or Ohm's law to solve for V3. However, let's use Kirchhoff's voltage law to do so. We know source voltage and V1 and V2. An algebraic rearrangement of the Kirchhoff's voltage law equation, solving for unknown voltage V3, suggests that V3 equals E minus V1 minus V2. Substituting our given values yields V3 to be the remaining 6.1 volts. As a means of checking our work, we can use Ohm's law to solve for I3. Substituting our value obtained using Kirchhoff's voltage law does indeed yield 20.3 milliamperes as we'd expect. P1 equals V1 times I1. Substituting our given values demonstrates that P1 is 231.7 milliwatts. We can use another permutation of the power equation to solve for P2, where P2 equals V2 squared divided by R2. Substituting in our given values yields P2 to be 376.4 milliwatts. We can use a third permutation of the power equation to solve for P3, where P3 equals I3 squared times R3. Substituting our given values demonstrates P3 is 124.1 milliwatts. Power in equals power out. P total equals P1 plus P2 plus P3. Substituting in our calculated values demonstrates that P total is 732.2 milliwatts. As a means of checking our work, supply voltage times source current also yields 732.2 milliwatts of total power. Let's now use Kirchhoff's voltage law to examine unknown voltage Vx. Another application of Kirchhoff's voltage law, starting here and traveling in the clockwise direction, demonstrates that E equals V1 plus Vx, where an algebraic manipulation demonstrates that E minus V1 equals Vx. Substituting in our given values demonstrates that Vx is 24.6 volts. Another application of Kirchhoff's voltage law, starting here and traveling in the counterclockwise direction, demonstrates that rise Vx is equal to the summation of voltage drops V2 and V3. Substituting in our given values similarly demonstrates that Vx is 24.6 volts. Given both analyses yielded 24.6 volts, I've got a reasonable degree of confidence our answers are correct, and we can move on to the next illustrated example. Our next illustrated example problem features a 20-volt source in series with a 620 ohm resistor and a 1 kilo ohm potentiometer at 3 different settings. In the first circuit, it's set to 700 ohms. In the second circuit, it's set to a maximum of 1 kilo ohm. And finally, in the third circuit, it's set to a minimum of 0 ohms. We're being asked to solve for the voltage drop across each element and the current through each element. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For the first circuit, the 20-volt source sees a total resistance of 620 plus 700 ohms, or 1,320 ohms, or more appropriately, roughly 1.3 kilo ohms. Source current is equal to supply voltage divided by total resistance. Substituting our given values demonstrates source current to be 15.2 milliamperes. Current through elements in series is the same. This is the most fundamental series circuit property. I source equals I1, which equals I2, and they all equal 15.2 milliamperes. An application of Ohm's law demonstrates that V1 will be 9.4 volts. We could use another application of Ohm's law to solve for V2. However, we can also solve for V2 using algebraic manipulation of the Kirchhoff's voltage law equation. The Kirchhoff's voltage law equation for this circuit suggests that E equals V1 plus V2. Substituting our given value for the source and our calculated value for V1 demonstrates that unknown voltage V2 is the remaining 10.6 volts. As a means of checking our work, an application of Ohm's law similarly demonstrates that V2 to be 10.6 volts. We can use identical techniques to solve for properties in the second circuit. With the potentiometer set to a maximum of 1 kilo ohm, the source sees a total resistance of 1,620 ohms. Source current is equal to supply voltage divided by total resistance. Substituting our given values demonstrates that source current has dropped to 12.3 milliamperes. Current through elements in series is the same. This is the most fundamental series DC circuit property. Source current equals I1, which equals I2, and they all equal 12.3 milliamperes. An application of Ohm's law demonstrates that V1 will be 7.7 volts. An algebraic manipulation of the Kirchhoff's voltage law equation demonstrates that V2 will be the remaining 12.3 volts. As a means of checking our work, an application of Ohm's law demonstrates that V2 is indeed 12.3 volts. We can use identical techniques to solve for these properties for the third implementation of this same circuit. With the potentiometer set to a minimum of 0 ohms, the 20-volt source sees only resistance of R1 for a total resistance of 620 ohms. Source current is equal to supply voltage divided by total resistance. Substituting our given values demonstrates that source current has increased to 32.3 milliamperes. Current through elements in series is the same. Source current equals I1, which equals I2, and they all equal 32.3 milliamperes. An application of Ohm's law demonstrates that V1 will experience all 20 volts. And an application of Kirchhoff's voltage law demonstrates that V2 will drop no voltage. As a means of checking our work, an application of Ohm's law confirms this suspicion. You'll note in this particular application, R1, the 620 ohm resistor, serves as a failsafe such that the source is always presented with an opposition of at least 620 ohms. Current at maximum can rise to 32.3 milliamperes. If, however, the potentiometer is increased to a maximum of 1 kilo ohm, the source can at most produce 12.3 milliamperes of current. All right, let's move on to the next illustrated example problem.